This lecture is for STAT219, Statistics for Biology. Today's topic is the Poisson distribution, which can be used to describe events that are distributed in time or space. So consider some events that are distributed randomly in time. For example, the number of cars arriving at an intersection each minute, the number of extinctions that occur per century or per year, the number of fatalities per month based on some criteria, car accidents, drug overdoses, etc., or the number of births per day at a hospital or in a city or across the country. These don't occur at regular intervals, but they occur with some average rate of arrival. There's an equivalent way of thinking about events distributed in space as if how many arrive or exist within a square area, like the number of raindrops that arrive in a square meter of Earth's surface, the number of foxes captured or living in a square kilometer, the number of diseased elm trees per acre, or any other thing that's like this also. They're not spaced regularly in space, but sort of randomly distributed with some average density. Both of these situations can often be described by a Poisson distribution. So here's what it looks like. It has an exponential formula involving factorial, but the basic idea is given some average arrival rate or average density in area. The Poisson distribution says how many we should expect in a random sample of that time interval or of that unit area. For example, if the distribution parameter says the average rate or average density is 10, then we should often expect to get 10 arrivals per unit time or 10 entries in a unit area, but we could easily also get 11 or 12 or 13 or 9 or 8 or 7. But if this is the average rate and we have a Poisson distribution, we very, very seldom expect to get 1, 2, or 3 arrivals, and also very seldom get more than 20 arrivals. And this, of course, is a probability mass function because it's only valid for integer values of x. We can't get 1.5 people arriving or 1.5 trees in an area. So it's a discrete value for my x, and so it's a probability mass function described by the Poisson distribution, just like the binomial distribution, which only takes integer inputs. So here's an example. You might recognize this from an old film if you're an old film buff. Suppose that the average murder rate by poisoning of husbands by wives in the US last year was 3.6 per week. Assume the number of poisonings is Poisson distributed, then the actual distribution might look something like this. We get a couple, then some space, and then one more, and then some space, and then a couple close together, and then a long space. This is the idea. The arrivals, or the rate of occurrence, averages 3.6 per week, but some weeks we get more than 3.6. Some weeks we get less. So we can compute probabilities on this with the calculator functions Poisson PDF, which will calculate the probability of getting exactly k occurrences, 0, 1, or 2, given that we first input the average rate, and Poisson CDF, which works just like the other cumulative distribution functions. If I use this one, it says what's the probability of getting k or less arrivals. So here's some uses of this function. If the average rate is 3.6 husbands bumped off per week, then the probability of 0 deaths in a randomly selected week is given by Poisson PDF, where I give the rate, the average rate, and the count of 0, and there's very small chance, only about a little less than 3%. The probability of getting 3 deaths in a randomly selected week would be Poisson PDF, where 3 is the count, and that has a fairly high probability, 21% chance. The probability of getting 4 or less deaths in 1 week is very high, since the average is 3.6. That includes, this will include 3 and 4, and also 0, 1, and 2. So the cumulative distribution up to and including 4, the answer is about 70%. And the probability of getting 5 or more, because the CDF only looks from the given number down, we have to use the complementary probability. That's 1 minus the probability of 4 or less, which we already calculated that part. So it's 1 minus 0.7, or about 30% chance of that happening. Okay, some characteristics of the Poisson distribution. It turns out that if the arrival rate is truly Poisson, then the average arrival rate is the same as the variance of the arrival rate, the square of the standard deviation. So in my sample, if the average number of arrivals is about the same as the variance of the number of arrivals, then the distribution is likely Poisson, and it will look something like this in time. If the variance is higher than the mean, significantly higher, we say the distribution is clumpy. There's long stretches of nothing and then clusters. And so this would not be Poisson, it would be overly clumpy. And if the variance is significantly lower than the mean, we say the distribution is dispersed, too regular. So there's something controlling the smoothness of the arrivals. So this is a basic test. If we want to apply the Poisson distribution, we want to verify that the average arrival rate is about the same as the variance of the arrival rate. So we've studied quite a few distributions up to this point. The normal distribution, where we have to know the mean and population standard deviation. It works for X bar whenever we have a sample size of at least 30, or we know that the original variable is normally distributed. And then the calculator functions, we use normal CDF for calculating probability of being in between A and B, or less than A or greater than A, I and V norm for calculating percentiles, and then Z interval for calculating confidence intervals, and Z test for doing hypothesis testing on the population mean, again, where we have to know the population standard deviation. More commonly, now we've been using the t-test and equivalently the t-interval to build confidence intervals. They're based on the t-distribution, which is the distribution of the sample mean, where the number of degrees of freedom is one less than the sample size. And we've been focusing here because when we use the student t-distribution, we don't need to know the population standard deviation. So here we're letting the data speak, and when we use a t-interval or t-test, we simply give it the sample mean and the sample standard deviation. We've also used the chi-square distribution, where its degrees of freedom is one less than the number of classes or number of parameters estimated. And it's the distribution of the sum of the weighted sum, we should say weighted by the expected value of the observed count minus expected count squared. We total those up, we get a number, and that number has a chi-square distribution, and we can do hypothesis testing using chi-square CDF from the statistic created here to infinity, or we actually have built-in functions in the calculator for doing a chi-square test directly or a chi-square goodness of fit test. We've also considered, as discrete distributions, first we considered the binomial distribution, the probability of getting k successes out of n tries with a fixed probability of success. For that we use binomial PDF, binomial CDF, and to test the hypothesis about the population proportion, the one prop z-test. And so today we're adding the Poisson distribution, the probability of k events occurring in unit time, or k occurrences in a unit of square space, where lambda is the average rate of occurrence in time or the average density in the space. And we have the parallel functions. Binomial PDF, the parallel function is Poisson PDF, where we give it the rate, the average rate, and then we can compute the probability of 0 or 1 or 2 occurrences. And Poisson CDF, the cumulative distribution, where we can compute the probability of 1 or less, or 2 or less, or 3 or less events in time or space, given the average rate of arrival. So here's a textbook problem, chapter 8.2, the count of parasitic nematodes on a certain freshwater fish. The way we work this problem, so we count the number of times a fish has 0 of the nematodes, or 1, or 2, or 3, or 4, and totals up to 6. And it looks like 103 of the sample had no parasites, 72 had 1 parasite, so this is a density occurrence, none per fish, 1 per fish, 2 per fish, etc. And the total number of fish sampled was 238. We can compute the average arrival rate by looking at the total except the first column, essentially multiplying each of these numbers together. If I multiply a count of 0 times 103, I get 0. A count of 1 times 72, I get a total of 72. So we're using the counts as weights and producing a weighted average. We total these up, and that's the weighted sum of 225 divided by the actual total, and we get an average arrival rate or average density of a little less than 1. And that makes perfect sense because most of the time, most of the fish have a count of 0, and many have a count of 1, and then the ones with higher counts drop off, so the average rate being close to 1 makes sense. So here we're estimating the parameter, and we want to see if it makes sense that this is a parameter for a Poisson distribution. Well, how do we test that hypothesis? Well, we look at the actual counts versus expected counts, and as always, we compute the expected counts by the total, 328, times the Poisson PDF. For 0, that gives me this one. So these are the expected counts under the assumption of a Poisson distribution with this as the average rate. And then we calculate our chi-square statistic in the usual way. The observed value minus the expected value squared divided by the expected value, and we run those through. So it'd be a good idea to pause the video and enter these as your list 1 observed values, these as your list 2 expected values, and verify my calculation of the chi-square statistic as observed minus expected squared divided by expected, and then totaled up. So if we do that, you should get a chi-square measure of 13.47, and then putting that into chi-square CDF from there to infinity with 5 degrees of freedom, since we have, 6 degrees of freedom, since we have 7 categories, will give a p-value of about 2%, less than my 5%, so that's sufficient to say that the typical H0, that the data matches the expected, is rejected, and then the distribution is not Poisson, would be the conclusion. Okay, so that's the background. We'll get to work examples of this in class.